Hello student, how are you? I'm Arun sir. Welcome to my channel Tuition Expert. Today in this class I'll teach you the radiation. Topics are emissive power, spectral emissive power, absorptive power, spectral absorptive power, and its Kirchoffs law and Stefans law and Kirchoffs law and Stefan-Boltzmann law. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the IITjee exam and NEET exam confidently with a good rank. Now let's start about the class. So topics are radiation. First, we learn what is radiation, how radiation energy is formed. We all know that hot body produces a radiation. A heat energy is produced from the hot body. If we keep our hand in front of a hot body, then we feel some heat. That is, we can understand that some radiation comes from this hot body. Now, theory is that all the body whose temperature is greater than 0 Kelvin, temperature is greater than 0 Kelvin or minus 273 degrees centigrade, produces the thermal radiation. That is, cold body also produce some thermal radiation. Now what is the cause of this thermal radiation? That is, all the charge particle which are in vibration produces the thermal radiation. Now all the thermal radiation is an electromagnetic waves. All the thermal radiation. What is thermal radiation? This is electromagnetic waves. Now for thermal radiation, every electromagnetic waves has a wavelength. The wavelength of the thermal radiation lies between 7.8 into 10 to the power minus 7 meter to 4 into 10 to the power minus 4 meter. Now this range is the infrared series. So every thermal radiation belongs to the infrared series, whose wavelength lies between these to these. So what is the source of radiation? All the vibrating charge particle in atoms or molecule of the hot body produces an electromagnetic waves. This electromagnetic waves is the cause of thermal radiation. The wavelength of the thermal radiation lies between these to these, which is called infrared series. Is that some property is that this is an electromagnetic waves. Thermal radiation is electromagnetic waves. First property, electromagnetic waves whose range is this. The thermal radiation obeys the law of reflection, refraction, diffraction and polarization. That is all the light waves. Property of all the light waves. This thermal radiation produces some pressure when it incident on a surface. Okay, so it exerts some pressure, that is, it carries some momentum, so it produces some pressure. And suppose this is a hot body, and at a distance d, the intensity of the radiation intensity of the radiation is proportional to 1 by d square. D is the distance of the point from the source. D is the distance of the point from the source. So intensity is proportional to 1 by d square, and hot body produces all the wavelength whose values lies between 0 to infinity. Okay, so the wavelength value of wavelength lies between 0 to infinity. So a hot body produces all the wavelengths whose range lies between 0 to infinity. So these are the property of a thermal radiation on a surface. We know, suppose this is a surface, when some heat is incident on a, when some heat energy or a thermal radiation is incident on a surface. Suppose this is total heat energy incident on a surface, then a part of its reflected, and a part of its transmitted, and some part is absorbed. So this is the total amount of heat energy incident on a surface Q, and some part is reflected QR, and some part is transmitted QT, and some part is absorbed QA. So total heat energy incident on a surface is Q equal to amount of heat energy incident on a surface for a given time. When we consider some energy, we assign a time range, because as the time increases, the amount of energy incident also more. So when we mention an energy, then we always mention a given time. So for a given time, Q is the total energy incident on a surface. Some part of this energy is reflected, some part of the energy is transmitted, like as the reflection of the light, and some part of the incident energy is absorbed here. So total Q equal to what? So total, now Q equal to this. Now what is QR? So here I write QR equal to reflected thermal energy. QR equal to reflected thermal energy. QT equal to transmitted thermal energy, and QA absorbed thermal energy. This. So we can say that Q equal to QR plus QT plus QA. Q equal to QR plus QA plus QT. Now we define three terms. First term is R, which is called reflectance. Reflectance is defined as the QR divided by Q. Okay, that is the ratio of the reflected energy to the total incident energy is called reflectance. Next term is T, transmittance. Transmittance is similarly QT by Q. And next term is A, absorptance. Absorptance is denoted by QA by Q. Okay, now if we add R plus T plus A, what we get? R plus T plus A equal to qr plus qt plus qa, which is equal to q equal to this, so which is equal to 1. So r plus t plus a equal to 1. R plus so r plus t plus a q. Now for perfect absorbed tense, now for perfect absorbed tense, for perfect absorbed tense t equal to 1, there r and a equal to 0, that is qt equal to okay. Now for perfect absorbed tense, a equal to 1, so r and t equal to 0, that is qa equal to q here. And for perfect transmitter t equal to 1, so there r and a equal to 0, that is qt equal to q. Now for perfect black body, what is the definition of perfect black body? For perfect black body, the body which absorbs all the incident energy incident on it, that is the body which absorbs all the incident thermal energy incident on it. So for perfectly black body, absorptance part, that is a equal to 1, absorb a equal to 1, that is t and r equal to 0, absorptance part is 1. This is perfectly black body. What is emissive power? Suppose this is a hot body, it radiates heat from all surface. Temperature is suppose T Kelvin. Temperature of the hot body is in absolute scale, that is in Kelvin scale, whose temperature is T Kelvin. Now it radiates the energy, thermal energy. It radiates the thermal energy. If Q is the amount of energy, amount of heat energy radiated in T second from whole the surface A, then emissive power is defined as Q by A by T, that is heat energy radiated per unit area per second is the emissive power, that is energy radiated so what is emissive power? Thermal energy, it is thermal energy radiated per unit area per second from the surface of a body is emissive power. So Q is joule, Q is unit of Q is in SI unit joule second, and area is meter square. So unit will be watt per meter square, watt per meter square. Unit will be watt per meter square, and dimension will be m t to the power minus 3. This dimension is m t to the power minus 3. M is mass, t for time, m t to the power minus 3. Now this is emissive power, that is heat energy radiated per unit area, that is thermal energy radiated per unit area per second from the surface of a body is the emissive power of the body. Unit is this and dimension is this. Now what is Stefans law? Now next term is spectral emissive power. What is spectral emissive power? What is spectral emissive power? Spectral emissive power, it is defined as the energy radiated per unit area per second for a particular wavelength. Particular wavelength defined as the energy radiated per unit area per second within a unit wavelength around lambda. That is emissive power. Normal emissive power is defined for all the wavelength, but it is defined as the radiant per unit area per second within a unit wavelength around lambda. That is E lambda is denoted by Q by A T in by lambda. That is energy per unit area per second per unit wavelength. So this is the difference between spectral emissive power and normal emissive power. Normal emissive power equal to Q by A into T, and spectral emissive power is Q divided by A into T into lambda. So this is spectral emissive power and this is normal emissive power. So its unit will be watt. Joule per second is watt per meter square, and angstrom, meter square angstrom. So this is the unit, and dimension will be, what is the dimension of the spectral emissive power? Dimension will be m t to the power minus 3 L minus 1. Unit dimension of spectral emissive power is this, because wavelength has the dimension length, so this is the dimension of spectral emissive power. Now and the relation between, as a hot body radiates all the wavelength, then we can define as E equal to E lambda d lambda 0 to infinity. So this is the relation between emissive power and spectral emissive power. E lambda d lambda, because E lambda equal to Q by A by T by d lambda into d lambda. If we divided d lambda, then this will be the E. So E lambda d lambda equal to, we get E. But as the wavelength is for small Stefans law is applicable for perfect black body. emissive power আমার তো এমনিতে বন্ধ হচ্ছে তো, না? What is Stefans law. This is applicable for perfectly black body. Emissive power of a perfect black body is proportional to the fourth power of absolute temperature. That is, emissive power is proportional to T to the power 4. That is, emissive power equal to sigma T to the power 4. Sigma is called Stefan constant. This is Stefans law. So this is Stefans law. E equal to sigma T to the power 4. That is, sigma equal to Stefans constant. Whose value is, the value of sigma is 5.67 into 10 to the power minus what, 5.67 into 10 to the power minus 8 watt per meter square, and the value of sigma is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So this is the value of sigma, and its unit and its dimension will be m to the power minus 3 theta to the power minus 4. This will be the dimension. The value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. K for Kelvin. K is Kelvin. So this is applicable for perfect black body. Now, so if a perfect black body, this is black body, perfect black body. So this is perfect black body whose temperature is T and surface area is A, and so if the Q amount, so if the Q is heat radiated in T second, Q is heat radiated in T second, so Q equal to sigma T to the power 4. This is energy radiated per unit area per second. So into area into T. This is the amount of Q for perfectly black body. Heat energy radiated in T second is this. Now, if for general body, if it is not perfect black body, for any general body, what is the temperature, what is the heat radiation through the area? Now for general body, we define a term emissivity. We define a term emissivity which is denoted by this. What is the emissivity? Emissivity equal to emissive power of any body, to the emissive power of black body. Emissive power of perfect black body. So emissive power, this ratio is defined as the emissivity. So for any now the emissivity has the value generally less than 1, greater than 0. Emissivity has the value greater than 0, less than 1 for black body. For perfect black body, emissivity equal to 1 for perfect black body, and emissivity equal to 0 for perfect polished body. Emissivity equal to 0 for perfect polished body. Okay, emissivity equal to 1 for perfect black body, equal to 0 for perfect polished body. So for a general body whose area is A, emissivity, whose area is A, emissivity, epsilon, temperature T in T second, total heat energy Q is defined as the Q equal to emissive power of the body will be sigma to the power 4. This is the emissive power of the body, because if this body would perfectly black body, then the emissive power of this body will be this if it to be perfect black body, but it is not black body, its emissivity is given, so the emissive power of this body will be emissive power of the black body into emissivity. So this is the emissive power of the whole body. Now if we multiply area into T, then we get total heat energy radiated from the whole surface in T second. So this is the one formula. If for any body temperature, area, time and emissivity is given, then total heat energy radiated per T second in T second from the whole surface is given by this. This is the unit. This is the unit joule or calorie, etc. Now next term is absorptive power. Now next term is absorptive power. This is A. So absorptive power is defined is the absorptive power is defined as the radiant energy absorbed by the body for a given time to the total incident radiant energy incident on the surface for that interval of time, for that given interval, for the same interval of time. We know the energy is time dependent. Energy absorbed or energy radiated is the time dependent. For a given time, we denote this time and this time will be same. So radiant energy absorbed by the body for a given time to the ratio of total incident radiant energy incident on the surface for the same interval of time. This ratio is the absorptive power. That is, for a particular body, suppose total heat energy is incident on the surface is 100 joule. Now among these 50 joule is absorbed, so absorptive power will be 50 divided by 100, that is half. If 100 joule energy is incident on the surface, and among this surface some deflected, some part is reflected, and some is energy and some is transmitted. So if the absorbed part is 50 joule, if 50 joule energy is absorbed by the body, then the absorptive power is defined as the absorbed part to the total incident energy is the called absorptive power. What is spectral absorptive power, which is denoted by A lambda? This is defined as the absorbed energy for a given time at a particular wavelength. Here wavelength is fixed, particular wavelength to the total heat energy, total energy, any energy, total energy incident, total energy incident for that interval of time, for that interval of time, for that interval of time, for that particular wavelength. This is defined as the spectral absorptive power, and a lambda equal to 0 to infinity and a equal to 0 to infinity a lambda d lambda. So this is the value, this is normal absorptive power and this is spectral absorptive power. Because 0 to infinity, because the hot body radiates all the wavelength whose range is from infinity, of all the wavelength whose range is from 0 to infinity. Of ratio of emissive power to the absorptive power is same for all the surface at a particular temperature, and each equal to the emissive power of perfect black body, emissive power of perfectly black body. This is called Kirchoffs law, ratio of emissive power, that is E lambda for a particular temperature, means particular wavelength. So we can mention any things, any between temperature, or we can mention at a particular temperature or a particular wavelength. So E lambda by A lambda, ratio would be same for all, is constant, which is equal to E lambda by A lambda for, this is for perfect black body. Now we know that for perfectly black body, A lambda absorb part is unity. For perfectly black body, absorb part is unity, absorptive power is unity. So E lambda by A lambda equal to E lambda, that is emissive power of the perfectly black body. E lambda by A lambda is constant. So E1 by lambda 1 equal to E2 by lambda 2 equal to constant, equal to E, that is emissive power of the perfectly black body. Now for a emissive power means a body how much energy radiates per second per unit area. A lambda, what is the absorbed part, that is energy absorbed. So E1 by A1 equal to E2 by A2 for a particular wavelength lambda equal to E lambda, that is emissive power of the perfectly black body. For a particular wavelength, this ratio would be same. Now from this, as the ratio same, that means if this be more, then this should be more, that is good emitter is also good absorber, good emitter is also good absorber, good absorber, because if this is more, then this should be more, as the ratio is constant. Good emitter or good reflector, good emitter or good radiator. Here one thing is that emitter is not equal to reflector. Emitter or radiator means radiator is not reflector. These are not same meanings. Emitter is not reflector. Emitter means emitter and or radiator is does not mean that it is reflector. Okay, this is not, this term and this term are not same, different meaning. Reflector and emitter are different meaning. Next term is Stefans Boltzmann law. Stefans Boltzmann law. Suppose this is a hot body whose temperature is T and surrounding temperature is T0. Surrounding temperature is T0. So some heat is radiated from this hot body, and or it also absorb some heat from the surroundings. It also absorbed heat. It also absorbs some heat from the surroundings. That is, emission and absorption take place side by side. Emission and absorption occurs simultaneously. That is, emission and absorption take place or occurs simultaneously. So if the area becomes A in T second, what is the energy emitted? So energy emission is equal to A into T. Suppose this is a black body, perfect blood, or if for any general body emissivity is given, emissivity into sigma T to the power 4. Sigma is Stefan constant, and Q absorption will be A into T sigma T to the this is emission part, this is absorption part. So net emission will be this minus this. So net emission will be this minus this. This, that is A into T. Net emission will be in T second, A into T, this A into T sigma T to the power 4 minus T0 whole to the power 4. Now Q by A into A by T is called net emissive power. Net emissive power. So net emissive power E net equal to sigma T to the power 4 minus T0 whole to the power 4, where T0 is surrounding temperature, T is body temperature. This statement is known as Stefans Boltzmann law. This is emissivity, this is Stefan constant. T is the temperature of the body, T0 is the temperature of surroundings. This is the net emissive power of the body, and this statement is called Stefan Boltzmann law. For remaining part, students, for remaining part of this chapter, watch my another video, and to get the more important problems of this chapter, you also watch my another video. Today is the end of the class. Okay, thank you.